let's first talk about a system. So consider a system AX equal to B, okay, or AX equal to Y, whatever. Now, this system, imagine that, as I talked last time about it, that imagine there is a economical situation, okay, so there is a economical process that when you model it, it becomes a system of linear equation actually, okay, becomes a system of linear equation. And imagine that this X in that economic model represents your expenditures. Okay, it represents your expenditures. So X is representing your set of expenditures, variables that are basically expenditures, and AX is equal to B. They satisfy this system actually. Now, what economists are interested in, they are not interested in all kind of expenditures, but they are very much interested in minimizing the expenditures actually. So the interesting question would be, what is the X that solves AX equal to B, okay, and has a minimum size actually, and has a smallest possible size. So what do you mean by the smallest possible? When a vector is going to have a small size actually. A vector is going to have small size if its components are small actually, or its magnitude is small actually. The more bigger a vector you have, the more magnitude it is going to have. So if X is representing what you call the expenditures, then I'm not only interested in those X which solve this problem AX equal to B, but I will be also interested in those expenditures, those X such that X has a minimum norm actually. Okay, and what do you mean by minimum norm? Okay, we defined it last time that by minimum norm I mean that any S, okay. So a minimum norm is a S, okay. So an S that solves what do you call AX equal to B, that is, it satisfies AS equal to B, and its norm, its magnitude is less than or equal to the magnitude of any X that solves this system. It's less than or equal to for all X that are the solutions of B. Okay, they are solutions of AX equal to B. Okay? For all X solving AX equal to B. So what do you mean by minimum norm solution of a system? That I want to find the solution of it, but this solution should be such that its norm is less than or equal to all other solutions of this actually. So economics people will be very much interested in what do you call such kind of problem, because they want to minimize our expenditures actually. So if you want to optimize anything, so it's like a minimize anything or maximize anything, minimize, for example, time for example the algorithm that works. So you want to minimize, say for example, processing time of for example for an algorithm or a process actually. Okay, all such models can be made in this manner actually. Anyway, so this is what that we are interested in. So keeping in view last result, so in last discussion we actually proved a lemma, okay, which I'm just going to write it again. I'm not going to prove it, okay, and then I'll move to the next important result actually. So it says that if V and W are finite dimensional inner product spaces, finite dimensional inner product spaces, and T is a linear transformation from V into W. Okay, so T is a linear transformation from V into W. Be a linear map. So it's a linear map. Then following is true. So what is true? That the kernel of the linear transformation would equal to the perp of the range of the adjoint of this transformation. Okay? So the kernel of transformation is the perp of adjoint of the range of the operator T. And you have a kind of a complementary relation as well, that the range of T, okay, is equal to the perp of the kernel of T star. The perp of the kernel of T star actually. Okay, this is what is really the lemma that we proved in our last discussion actually. I'm interested in a particular kind of a form of a lemma actually. Okay, so if I choose particular, what do you call inner product spaces in a particular transformation, what would be the interpretation of this? That's what I'm interested in actually. So take nu to be, what do you call, Fn. Okay, so it could be Rn, Rcn. Okay, Rn, Rcn, and take W to be, what do you call, Fm. Okay, so it's a cross product of Fm times, where F is a field of real numbers, R complex number. And consider a matrix from, what do you call, that has an order, say m by n. Okay, that has an order m by n with entries from, what do you call, F. Okay, so if A is a matrix of order m by n with entries from F, then this matrix will induce a linear transformation. We know that every matrix induces a linear transformation, and every linear transformation, especially in finite dimension, every transformation induces a matrix actually. So corresponding to a matrix you can find a linear transformation, and corresponding to a linear transformation you can find a matrix actually. So it induces a linear transformation from nu to W, okay, from Fn to Fm, such that Ta operated onto some element x, where the x is from, what do you call, nu, so it's an element in Fn, would be equal to A multiplied, so how a transformation and its matrix are related. So Ta operated onto x is equal to the matrix A multiplied by, what do you call, x actually. Okay, what do you call x? Then this Ta is a linear transformation for sure. Okay, this Ta is a linear transformation. So you took matrix A, so this matrix induces a transformation, linear transformation corresponding to A that looks like this. Now I want to interpret this result in the terms of, what do you call, this linear transformation. Now let's talk about, what do you call, what would be the kernel of T. Okay, the kernel of T is going to be the collection, or the kernel of Ta. Okay, the kernel of Ta is going to be the collection of all x, okay, such that Ta is operated onto x is equal to 0. Okay, and this is same as x such that A multiplied with x is equal to 0. And therefore I can call it that this is the null of the matrix A actually. Okay, the kernel of this linear transformation TA is equal to the null of the matrix A. So what is the null of matrix A? It consists of those vectors from V, in other words Fn, such that Ax is equal to 0, which are kind of annihilated by A. Now let's talk about, for example, range of T star. Okay. The range of T star is going to be the collection of the images, okay, TA star, sorry, the images from, what do you call, by the way, let's first, before getting into it, let's first talk about the adjoint of this induced linear transformation. So what would be the adjoint of this linear transformation? So we have talked about it previously, that how to find the adjoint for a given linear transformation. So the adjoint corresponding to this linear transformation is going to be a map from W to V, nu, okay, or V. It's going to be a map W to V such that T star A when operated onto, say for example, a vector y from V, okay, this would be equal to the A star, what do you call, A star operated onto y actually. It's going to be the A star operated onto y. So in other words, T star A, okay, so I can also say that the conjugate operator of A is basically what the linear transformation induced by the matrix A star actually. Okay, so the adjoint of the linear transformation TA is equal to the linear transformation induced by the matrix A star. So this is going to be the meaning of the adjoint of, what do you call, the linear transformation TA actually, where A star is the conjugate transpose. Okay, so it's really the standard conjugate transpose of the matrix actually. Now once we have this description, now I can write, what do you call, the range of the range of T star, TA star. Okay, so the range of T star A star is going to be the collection of all outputs of the y's from the W. Okay, take a y from W, in other words Fm, and operate, what do you call, T star A onto them. Okay, so it will be the collection of the all outputs actually. Now if this would be the case, then this is equal to, what do you call, the A star Y of Y belongs to W. Okay, this is what it is going to be, because TA star Y is really equal to the A star Y. Now what is A star Y? So there are many ways that you can interpret this what do you call, set in different ways, but one of the way would be that this is really the column space of the matrix A star actually. Okay, so by computing the A star operated onto A, what you're gonna get? You're gonna get the all vectors that are spanned by the columns of A star actually. Okay, so what do you mean by the column space of a matrix A? Okay, so if a matrix A has columns, say A1 up to AN, okay, by the column space of a matrix I mean a span of the vector, a span of the of what do you call, the vectors A1 up to AN actually. So this is going to be the column space of A, and the column space of A star is going to be the collection of those vectors which are the linear combination of the columns of A star actually. Okay, so the columns of A star. Take the columns of A stars, and the subspace is spanned by those columns is going to be the column space of A star actually. So this is really the range of TA star. Now keeping in view this result, what does this result shows? So I can interpret this result as that this is equal to, this says that the null space of A is equal to the column space, the perp of the column space of A actually. Okay, the perp of the column space of A. So if you have null space, so if for example this represents the, say pictorially, this is the plane that consists of all those vectors which are 0 under A, okay, then the column space of A is the collection of all those vectors, okay, the collection of all those vectors which are orthogonal to each vector here actually in this space, are, all vectors that lie in this space. So these vectors are orthogonal to each one of these vectors actually. So column space of A star perp contains all those vectors which are orthogonal to what you call the null space of A actually. Okay, so you can interpret it in this manner. So if this is the null space of A, then this pictorially can represent what you call the column space of A star. So the vectors in null space are orthogonal to the vectors in the column space actually. Okay, so that would be one way to make sense of it. The other can be represented in the similar manner is that the column space of A, okay, so this result can be interpreted as the column space of A would be equal to the null is, take the null space of A star and consider its perp. Actually. So this is what is going to be really the interpretation of this result actually. Okay. Now using this notation, okay, I want to, what do you call, write a very interesting theorem actually, and I'll show that theorem pictorially as well. That theorem is going to be the theorem about finding the minimum norm solution of a given system of equations that allows you. So that theorem is going to give you a method actually for finding the minimum norm solution. So here's a theorem, okay. You can treat it as an algorithm for finding the minimum norm solution actually. So suppose your Y is from Fm, in other words the space W that we called, and A is a matrix that is an m by n matrix with entries from F actually. Okay, so this is an m by n matrix with entries from F. Okay. Now, and suppose that this system Ax equal to Y is a consistent system. So suppose that you have a system for which you have a solution actually. Okay? So it is a consistent system. So for the consistent system you have two possibilities. So one possibility is that it is either it has a unique solution or it has infinity many solutions. So if a consistent system has a unique solution, then since there is so that solution is also going to be a minimum norm solution because there can't be any other solution actually. Okay, so if a system has a unique solution, then that solution is going to also be the minimum norm solution. But if the situation would be more interesting actually in the case when the system has infinity many solutions actually. then you can ask the questions that, okay, out of all these infinite, what do you call, solution, which solution of this has the minimum norm? So that's what is really the key thing that we would like to do. So here's the part A of this. Let's call this equation star, system star. So if you have a system that is consistent, then you always have a minimum norm solution. So the minimum norm solution always exists actually, okay, and a unique minimum norm solution. So the system, okay, the system star has a unique, so this is important, unique minimum norm solution. So the first part kind of guarantees that if you have a consistent system, you're always going to have a minimum norm solution, and that solution is going to be unique. In other words, you can't have more than one unique, what you call minimum norm solution. Okay. B is this. Okay, so there is another thing. Moreover, if you want to find a minimum norm solution, let's call this solution S actually. Okay, so the minimum norm solution S. Moreover, this minimum norm solution, this S, lives in the kernel space of A star actually. Okay, column space of A star. So this minimum norm solution, if you want to find it, okay, this is going to be in the column space of A star. Okay, this is what is the case. So what is the B part? So here is another interesting thing. F is unique in two perspectives. So S is unique in the perspective that it is a minimum norm solution, but it is also unique in another perspective, and that perspective is that F is the only vector in the column space of A star that satisfies this solution. It's the only vector, so it's the only solution that is a solution, and it sits in the column space of A. So S is the only solution. You can't have any other solution. Only solution of a star, okay, that lies in column space of the matrix A star actually. Okay, column space of the matrix A star. So here's the third thing. So again, so S is unique in two manners. It's a unique minimum norm solution, and it lives in column star of A star. So not only it lives in column of the space of A star, but it's the only vector in the column space of A star that solves it. You can't find any other vector in the column space of A star that solves this system. So it's unique actually. And the third part is that if you take, for example, a system A star U equal to Y, okay, A star U equal to Y, then this system is consistent. This system is consistent. Okay, and this is going to play a very important role in finding the minimum norm solution. So this system, so if you take A product of A star operated onto some vector U, okay, in obviously Fm, okay, then this equal to Y has a consistent solution actually. Now it's consistent. And if if it is consistent, then it must have a solution actually. Okay. So let's take, say, U naught from Fm. That is a solution of this problem. So if U naught in Fm is such a vector such that A star U naught equal to Y. So in other words, imagine U naught is a solution to this system. Then using this U naught, you can find very easily what do you call this this minimum norm solution actually. Okay, then so it's pretty important to understand the precise statement of it. And so if U naught is from Fn such that it solves it, then F, the minimum norm solution, is going to be equal to A star U naught. S equal to A star U naught is going to be the solution, okay, that really, what do you call, it's the minimum norm solution. Okay, so let me give you an interpretation, and then talk a little bit about what do you call each part of it. So I have a system that is consistent. So you can ask a question, is there always a minimum norm solution? The answer is yes, there is always a unique minimum norm solution. Secondly, where to find this minimum norm solution? So you're going to say, if you want to find this minimum norm solution, go and search in the column space of A star. Okay, go in the column space of A star. So in other words, the first part tells you that it has a solution. The second part tells you that this solution lives in this space. The third part tells you how to find that solution actually. Okay, how to find that solution. So the algorithm to find that solution is, first solve this system, A star U, use some abstract vector equal to Y, where the Y is same Y. Solve this. Once you have a solution of this system, say U naught is the solution of this system, just multiply this U naught with matrix A star, okay, then this is going to be what do you call a minimum norm solution of Ax equal to Y. So first solve this system, okay, and once you have a solution of this system, multiply this solution with A star, and that is going to be the minimum norm solution actually of your given system. So the third part gives you the algorithm. First part tells you there is a minimum norm solution. Second part tells you that it lives where? It lives in the column space of A star, and it is the only vector. It is the only vector. And you can see that since S is the only vector that lives in the column space of A star, and if you say where is going to be the A star U naught? A star U naught is what do you call vector, okay? A star U naught is a vector that is in the column space of A star actually. Now A star U naught solves Ax equal to Y actually. Why? Because if I take my A and operate say A star U naught into it, so that would be equal to Y. So this A star U naught solves Ax equal to Y. And this A star U naught also belongs to the column space of A star actually. But F is the only solution that lives in the column space of A star. And A star U naught is another solution of the, this system Ax equal to Y that solves what do you call Ax equal to Y. So these two solutions can't be different because S is unique actually from the part. I'll prove it actually in a moment. I'll prove it in a moment actually.